Let's jump right back in. We've been talking about some trade-offs in thrust and efficiency. Remember, for the launch vehicles, you get a lot of thrust, but with a low specific impulse, right? Low efficiency. Whereas for, say, it's ion engine, we could get small amounts of thrust, but very high, or relatively speaking, high efficiency, a high specific impulse. Let's talk about stability. This actually works exactly the same as it does for an airplane. Everything we discuss applies. It's a bit simpler in this case, but it's the exact same concept. So recall, for longitudinal static stability, right, so we have this airplane flying, thinking about this pitching motion. What is my requirement for static stability? You may recall that I need to have my center of gravity in front of the aerodynamic center. Okay, so it's in front of, for a rocket, because we're going vertical, same thing, but we say the center of gravity needs to be above the aerodynamic center. That's the same idea here, right? So let's say here's my rocket, and I've kind of exaggerated it. Say this was my free stream velocity, so this would be the angle of attack. That's going to be undesirable. I want my rocket to be essentially at 0 degrees angle of attack the whole time. Even when I'm changing my heading angle, right? So my rocket's flying like this, it's still close to 0 degrees angle of attack the whole time, right? Because the free stream is in the direction that it's flying. This would mean that I was flying up, but I was tilted, right? So I'm kind of flying like this, an angle of attack. I don't want that for a rocket. That's going to be bad for performance, and it's going to be dangerous if I'm unstable. So for stability, right, if this angle of attack increased, if I deviated, I would love for it to return automatically, right? I want this to be statically stable, or that could be a real problem. So we already talked about the criteria, but let's just illustrate this again. So let's say here's my CG, and it's my center of gravity. What are the forces acting on here? Well, imagine turn your head sideways, right? This is basically like a big plate or something going at an angle of attack. So I'm going to generate some lift perpendicular to V, and I'm going to generate some drag in the direction of V. And remember the right-hand rule, if I want to find a moment, that's going to be R cross F, and R is from the CG to these force, right? So from here to here. So I go R cross F, and for both lift and drag, it's creating moments in the same way. My thumb is pointing out of the page there, so that's going to be a counterclockwise rotation. My rocket's going to come back. So if I deviate, right, if a gust hits me and I get off course, if my airplane is stable, it's going to come back, right, and go back to that 0 position, which is what I want. So my center of gravity is in front of, right, in front of, we're thinking about an airplane, or we could say above the rocket, same idea. Center of gravity is above my aerodynamic center. The only slight difference in how you usually hear it is, remember, we spent a fair amount of time discussing the difference between aerodynamic center and center of pressure. Remember, the center of pressure wasn't super useful for us because it moves around as angle of attack changes. Whereas the center, the aerodynamic center, by definition, doesn't move with angle of attack. So it was a nice reference point. For a rocket, the angle of attack is always going to, almost always going to be really close to 0. So we generally don't worry about that distinction because the center of pressure, yes, in principle, it does move around, but because we stay right by 0, it's hardly moving at all. So most commonly, you'll hear people say for stability that the center of gravity needs to be above the center of pressure. But if we're being, more careful, it's really the aerodynamic center that matters. But it's just that it doesn't move very much for a rocket. So that's what you'll typically hear. Okay, so let's derive what's called the rocket equation. This is going to be analogous to the Breguet range equation. You may remember when we're looking at an airplane range, we looked at how much fuel we're burning per unit time, right? And we kind of integrated forward. We came up with a differential equation. We assumed some things were constant and came up with a simple closed form expression for range. We talked about how that's a useful expression to understand trade-offs, and it is. It's not as useful, it's still kind of useful, but it's not as good as doing an actual integral, right? Because a lot of those terms like L over D are not actually constant. The same thing's going to apply here. We're going to look at how our fuel is burning and how our velocity changes. And we'll have a differential equation, which in general we want to integrate, but we'll also do a symbolic integration, assuming some things are constant to help us understand better how things trade off. So perhaps the best way to do this, I think, is from a fluid dynamics perspective, looking at a momentum balance. But That requires maybe slightly more intermediate fluids that maybe some of you haven't taken. So we're going to do it with Newton's second law. You can do this just fine. You just have to be a little careful sometimes on what you treat as a system and whether you treat the variable mass as an external force or not. It depends on the form you use. But what we're going to do is we're going to look at some of the forces being equal to change in momentum per time, dp dt. And we're going to consider the momentum of the full system. So I've broken this up into the rocket, everything except for this little piece of fuel. I'm actually going to call it delta instead of dm. So some little piece of fuel that some instant in time later is going to be burned and expelled out the back. So they're still the same total mass, but they've now separated. So initially, these are together. We're moving with speed v. And so my initial momentum is going to be m plus delta m times v. Okay, at another next instant in time, some little time later, I'm going to be moving at speed v plus delta v. I don't know what delta v is. I just know that, in general, I'd probably changed a bit. And at the back, my mass is going to be accelerated at speed c minus v. So c was that effective exhaust velocity we talked about last time, because that's how I'm expelling this out of my rocket. And I have to have the minus v because I need to go into my inertial system, right? So it's relative to the rocket. So if c was equal to v, right, my rocket's moving up at speed v, and I'm sitting here as an observer just watching it. If I expelled it at just speed v, I'd cancel out just the speed of the rocket, and it'd be like that propellant would just be sitting there, right, as the rocket going away. So I need to expel it out faster. So that's going to be the c minus v. So my final momentum is the blue part, m, v plus delta v, and the red part, moving down, I've got a minus, delta m times c minus v. Okay, so those forces are going to be my final momentum minus initial momentum over the change in time. So I'm just going to expand each one of these terms. So for final momentum, I've got mv plus m delta v, now doing this next term, right, minus delta mc plus delta mv. And now I got to subtract off this initial momentum minus mv minus delta mv, and that's all over delta t. So we can see that some terms cancel. There's an mv here that cancels with this minus mv, and there's a delta mv that cancels with this minus delta mv. So I'm left with m delta v over delta t minus c delta m over delta t. Okay, so I take the limit as dt goes to 0, these become differentials. But one thing I got to be a little careful of, that I didn't do this in the textbook, but the end result was right, but I wasn't clear on this step. This just becomes m dv dt, or this is kind of the ma term. We're used to F equals ma. This other term is occurring because I've got a variable mass system here. I've done this generically as a system, right? They're just two bodies that are moving apart. But I want to write this equation from the perspective of the rocket, the blue part, right? And in that sense, the mass dm dt is decreasing, it's negative, right? Dm dt is negative, so I need an extra negative sign here. So this dm dt is negative of what I've written before, so I've got this plus here. So let me write this out again. We've got F equals m dv dt, so ma term, plus this extra term, c dm dt, where c is that effective exhaust velocity again. So it's how fast I'm exhausting it relative to my rocket. Okay, so what are the forces that are acting on the rocket? Right, this is equal to sum of the forces. I'm going to draw a generic case where the rocket's has some different heading angle. So here's my rocket, say, right? Some plume here. Here's V infinity. It's at 0 degrees angle of attack. It's aligned, but it's not vertical. I don't have to have vertical. So this theta is my heading angle. It's not the angle of attack, right? That's still 0. That's just my heading angle. So my rocket can be here, right? So I've got weight, of course, mg acts down, and then drag is going to act in the direction of the infinity. I've derived this equation here, this part, right, in this coordinate system aligned with the rocket. So that's in the direction of B, but I only get a component of mg. It's mg cosine theta, only a component acts. So this is going to equal to, and these are in the minus direction, the way we've derived this. So minus mg cos theta minus d. Those are the forces. Okay, so in general, well, actually, let me just do one more step here. I'm going to multiply everything. Well, actually, first before that, I'm going to ignore drag. Drag is important, of course, but it's relative to the other terms, a much smaller contributor. So for this basic analysis, we're going to ignore it. But, you know, like I said, this is maybe 5% or so. It depends, but it's going to be a smaller term. Okay, so I'm going to ignore that. And then what I'm going to do is I'm going to multiply through by dt. So it's going to, oops. It's going to cancel here and here. I'm going to have a dt over here. I'm going to divide by m. So it's going to cancel this one with this one, and I'm going to have an m over here. So I'm going to try and do that in one step. So I'm going to get dv equals, and I'm moving this to the other side too. Sorry, I'm doing lots of steps at once. Minus c over m dm minus g cosine theta dt. This one is a dm. Sorry, dm. Okay, so sorry, I did several steps there just to recap. I took this one, moved it to the other side, so there's a negative sign. I multiplied everything through by dt, so that's gone, and there's a dt here. That's good. I divide everything by m, so that's gone, and I've got an m in the denominator here. So I think I did that right. Okay, so now I'm going to integrate everything from the start of my ignition till I burn, or whatever stage this is. We'll just call it 0 to burn time, TB. Okay, and ideally, this is where I would do a numerical integration, right? Because some of these terms are going to change, but for purposes of getting kind of a rough equation to see how these factors contribute, we're going to assume some things are constant. On this side, this just becomes delta V. This is how does my velocity change? You know, it's 0 at the beginning. What is it at the end? And it may not be 0, right? So I may be looking at a second stage of the rocket where I start from already some speed. But anyway, this is how much my velocity changes. I clearly cannot pull m out of the integral. My mass is changing. That was the whole point of this analysis, is that I was burning fuel. So m is changing, but I can assume that c is constant. It's not really constant, but it's, you know, it's fairly close. That's not too bad. So this is going to be minus c. This term here is going to be a natural log. I'm going to go from initial to final. So I'm doing several steps here at once. The integral of dm over m is the natural log of m. I integrate from initial to final. And so that gives me m final to initial, but I got a negative sign, so I can flip that. So that gives me initial over final. I'm using the rules of the log, right? Where if I subtract two things, it's the same as dividing in the argument of the log. Sorry if I did that too fast. Just you know, write it out. See that. So here, this term g is not really constant, right? Because I'm moving further away from the center of the Earth, so gravitational acceleration is certainly changing. And if theta is important, then it's almost certainly changing. So that's really not good either. But let's just pretend, you know, just for, because actually this term also is, it's not super small, but it's much smaller than this term. So I'm actually just gonna, well, actually, let's just leave it. Let's ignore it. So let's say if you wanted to include this, you should probably do the integral. But if you're trying to do a first order analysis and we don't care about, you know, we just want to kind of understand roughly about where we're going to be, and this is good enough. So what does this equation say? Oh, sorry, the negative sign is gone because, well, all right, let me just do that more carefully. So this becomes minus c, the natural log of m from initial to final. Okay, so that's equal to minus c, the natural log of m final minus m initial, which is equal to c, the natural log of m initial minus the natural log of m final. So then I have delta v equals c, the natural log of, and I'm using the log rules here, right? If I subtract these, I can put them in the same argument, divide them. Okay, and we call this term here the mass ratio. So I'm just going to write this in this final form here. C natural log MR, mass ratio. So it's a ratio of my initial mass to my final mass. The final mass is going to be lower, obviously. So this is that rocket equation. Tells me what matters, so I can look at what type of delta V I need to achieve. C, remember this is my effective exit velocity, is going to be a function of my propellants, what type of, how energetic are these propellants. So different types of, say, fuels are going to change this. And the mass ratio, how efficient is my structure? Is it, I would love to have it mostly be propellant, right? I got to have some structure, obviously, but the bigger this is, the better, right? So if I can burn a lot of the mass away, this is going to be better. So this kind of tells us how these things compare. And they can also give us an idea about the magnitudes. So for example, to get into low Earth orbit, it takes a delta V of about 9 kilometers per second. That's what I need to achieve here if I want to get to low Earth orbit. That's actually quite a bit. So I mean, so getting out of Earth's, getting away from Earth takes a ton of energy. So by contrast, to get to Mars is actually not that much more delta V. It's like 10.4 or something like that, right? So whereas it takes 9 kilometers per second just to get to low Earth orbit. So the most energetic propellants we have, this is like 3 to 4 kilometers per second. That's what C is. So we can solve for what mass ratio we need to get this to get up to be 9. And it turns out it means we need to get to be about 90% propellant, which is amazing. And in fact, that's where the rockets are. But if you think about that, and this is why, we talk about airplanes and how we obsess about weight. With rockets, we way obsess about weight, right? Like this is just, it's really, really important that we get that because of this equation. If we want to get out of the Earth's atmosphere, even the best propellants that we have, we've got to have a rocket that's like 90% fuel. So compare that to an airplane, right, where it's more like 50%, 45, 50% is fuel, and a car, which is like, it's like a few percent of your car is fuel. So for a rocket, we've got to be extremely efficient. That's also not just a challenge, but it's a downside in the sense that it doesn't leave me much room for payload, because in that remaining, 10, 15% or whatever, I've got to have all the structure and then all the payload. And the whole purpose of the rocket was to deliver that payload. But to make that happen, to get it out there, I've got to have massive amounts of fuel and then as minimal structure as I can to make that happen. And so payload, so for example, the Saturn V, its payload fraction, meaning how much payload, the mass of the payload relative to the mass of the whole rocket, is 4%. And the space shuttle is about 1.5%. So, again, the whole point was to deliver that payload, but you need like tons and tons of just propellant to make that happen, to only deliver this small, relatively massive I forgot what I was saying, but payload anyway. So, this equation kind of highlights the challenges. It also helps us realize that, we're really fortunate that the Earth isn't much bigger, because if it was, the delta V we'd have to get is even bigger, and the whole space flight may not even be possible for us. Depending how big it is, because based on the fuels we have, our best that we've got, we still we can barely do this by having the rocket, our most efficient thing, and only deliver the very small amount of payload. A little further, right? This is actually kind of exponential. Notice it's a log term. If I took this as an exponential, right? If I solve this for the mass ratio I need, it's going to be this delta V over C. I'm going to have an exponential. So there's exponential term. So if delta V starts getting bigger and bigger, right? I just need tons of, that just becomes impossible at some point. But, fortunately, once we get out of low Earth orbit, getting to other places is not nearly as difficult. Okay, so let's talk about staging. This is going to be the last thing we talk about today. Staging also helps us with this kind of problem. And to illustrate this, let's just talk about this 2-stage rocket here. So here at the top, this is the payload. This is what we care about. I'm going to write with, let's call it the pay for payload. And I've got two stages here. So this is my first stage. It's gonna burn. And after we burn it, we're gonna get rid of this whole structure. So we're gonna shed this. You've probably seen some rocket launches, right? Where we start shedding parts. This is what it means to have these different stages. So this is gonna be the mass of the propellant for stage one. So P1, propellant one. And then this gray part, this is gonna be the mass of the structure for stage one. It's also sometimes called the inert mass. We'll just call it structural mass. So this is the structure for two, and then this would be the propellant for two. So my initial mass, right, the mass that I start with, is going to be all of these things combined, right? The mass of propellant one, mass of the structure at one, plus the propellant for two, plus the structure for two, plus my payload. That's my starting mass. So let's go back to this equation. I need to, this is going to be my fuels. I need to figure out what my mass ratio is. So that's, remember, initial over final. So I'm going to do just for stage one, what's my mass ratio for stage one? Well, when I start, it's M initial. That's where I started. What is my final mass at the end of stage one? See if you can write that down. Well, it's M initial minus the propellant mass, right? So I burned off that propellant, okay? So the change in velocity I get for stage one is C, which didn't really derive this. This is just based on the, well, I'll just keep it this way. Let's just say it's C. Incidentally, C is the same as G times the specific impulse that we talked about. If you just go back to what the definition, let's just go back real quick. All right, here's the definition of specific impulse. If I put G, move it over, I get thrust over m dot f. And if we look here, thrust over m dot f, that equals C. All right, so we often write that more because ISP, the specific impulse, is maybe more fundamental. So I'm just going to actually write that. G ISP times the log of that first mass ratio. So here I'm just using the rocket equation for stage one. Okay, now let's do stage two. What's the mass ratio for stage two? What's my initial mass? Take a second and write that down. It's M initial. It's not just M initial minus the payload though. I got to get rid of the structure. So this is the one point that you got to be careful on, right? At the end of mass ratio one, I burned all of this fuel, this blue part, I burned all the propellant. I do toss off the structure at the end, but that's not helping me with this mass ratio, right? It's not like that gave me some thrust. That's just something that happens at the end of the stage. I toss it off. So it doesn't go into this mass ratio term. But when I start the second stage and I'm burning, that's gone, right? The structure is gone. So my initial mass doesn't include that, okay? So now I've got M initial, right, minus MP1, minus MS1, minus MP2. So then the velocity change for that second stage is going to be GISP times the natural log of that mass ratio. And the total velocity I achieve is the sum of both of those. Okay, so we just did the math, but let's think conceptually. Why would we want to do this? Well, you could think that it's kind of like we talked about fuel burning rocket or fuel burning aircraft, right? As we burn, that's actually going to make us lighter. So that's actually better than just the battery where we, from a structural perspective, where we use some of it up, but we still got to carry that part. So if we burn all this fuel, we want to get rid of a big piece of structure. So now I've got this lighter rocket that I'm dealing with. I'm not carrying around a bunch of dead weight that I don't need. This is actually pretty helpful. To show you this, will be the final thing to look at. Let's look at this graph. This is just an example, right? These numbers are going to vary depending on what you see. But in this case, we're making an assumption the rocket is 90% propellant. That's pretty optimistic. That's about the best we've been able to do, close to that. So the rocket is 90% propellant. That means the rest, structure, payload. The specific impulse is 350 seconds. That's the high end for like a chemical rocket. That's about the best of the propellants we have. So 350 seconds ISP. And we're trying to get to low Earth orbit. So that delta V we want to get to is 9 kilometers per second we talked about. So if we make those assumptions and we do this optimally, this is what happens. Notice that for one stage, this on the y-axis is telling us how much payload we can carry out of that, out of a rocket. For one, you'll notice there's no dot. What that's saying is we can't do it. If we want to get to low Earth orbit, it's impossible with even a really best, some of our best propellants and a 90% propellant rocket. We cannot get to low Earth orbit with one stage. Or we get to a lower altitude, something else that we want to do. But if we want to go to low Earth orbit, too bad, can't do it. We can do it 2 stages, right? By tossing it off, we get to 2 stages. So it's possible, but notice we can only carry, our payload is only about 3.5%. And if we go to more and more stages, this gets better and better, but you see the returns are quickly diminishing. Incidentally, this is why most rockets you'll see are 2 or 3 stages. Every time we bump up, we're adding complexity, but we're not getting much more benefit, right? If I go to 4 stages, just add more complexity, but I only got a teeny bit more out of it. So usually, there are some that exist, but most of the time, it's a 2 or 3 stage rocket. And you'll also notice that, right, I'm kind of getting only around 4.5% of my rocket is payload, which, it's about where the Saturn V was. So this is the main challenge of rocketry, right? It's amazing how we can do it, but it takes a ton of fuel, and we can only deliver a little bit of payload, so you got to be very, very efficient structurally. Okay, so that ends it for today. Next time we'll start talking about propulsion for rockets.